There is no question that 3D printing is radically changing how we make things. 3D printing allows quick, painless prototyping and small-scale manufacturing, even for parts that would be difficult to produce with conventional techniques like machining, casting, or injection molding. The Auburn Cyber Research Center is equipped with a state-of-the-art FDM 3D printer which features a dual extruder system for printing soluble support material. Many designs contain overhangs and bridges, which are extremely difficult to print because the hot filament will sag or fall down. Most printers solve this by printing supports which act like scaffolding to hold up the overhanging features in your part, but this has to be removed by hand afterwards, which is tedious and time-consuming. Our 3D printer's dual extruder system solves this problem. We still use supports to print complex parts, but the support structure is printed in a special secondary material. Once the print is finished, the part is placed in a chemical bath, and after a few hours, the support material has been completely dissolved. This gives us beautifully finished parts without the need to manually clean off supports. But these machines present a difficult security problem. Most are connected to networks, and some are even controlled via cloud services, so we have to worry about keeping them safe and reliable.
One of the ways a part can be compromised is by modifying what's called the infill. Most 3D prints aren't solid plastic. They have a honeycomb structure called infill. So this part is 10% infill, which means 10% plastic and 90% air. A lower infill setting can save time and material and thus money, but it also makes the part weaker. If an engineer requests a print with 50% infill, it wouldn't work out if the printer churns out a part with 20% infill because that's less plastic going into the part, making it much weaker. But the worst part is that the engineer couldn't tell the difference. It would look exactly the same from the outside.
To demonstrate this kind of attack, we've printed two brackets, one with 50% infill and one with 10% infill. Otherwise, they're identical. Watch what happens when we hang a 50-pound weight from each one. So how could we prevent an attack like this? Well, it's not as simple as it seems. One thing we could do is encrypt the network communication between the printer and your computer. In theory, that helps a lot. But in practice, it's very difficult to bolt on security features like this without messing up workflows and making the printer inconvenient to use. Properly securing 3D printer communications is going to require a cooperative effort from all parties involved, from printer manufacturers to CAD software developers to the engineers themselves. But simply encrypting the traffic isn't the only thing we can do.
One of the reasons it's so easy for an attacker to modify a print before it gets to the printer is because the printer doesn't actually see the whole model. The printer doesn't get a 3D CAD drawing. Instead, it just gets a set of step-by-step instructions called G-code that describe how to move the printhead around to actually make the part. So it's actually very difficult to detect when the G-code has been tampered with because the printer doesn't know what the end result is supposed to be. It just knows how to follow the instructions. To understand this, imagine someone handing you a recipe that you've never made before and not giving you any pictures or any instructions otherwise. You might see the ingredients and the steps, but you don't have any idea what the end product really should look like.
For the printer to really understand instructions, we have to use a process called TSAT, or Toolpath Static Analysis Testing. This is basically a complex computer program that knows what to expect and tries to detect patterns that seem out of place. For instance, TSAT might know that the printer can only handle nozzle temperatures up to 250 degrees. If it receives G-code asking for a 350-degree nozzle temp, the TSAT routine will raise a red flag. If you've got a part that you print pretty often, the TSAT program might know it should take 4 to 6 hours to print, depending on the exact settings from the engineer. If it receives G-code for that part that will only take 2 hours, it will assume something isn't right. Now, obviously these are oversimplifications, but they show the idea. To go back to the recipe metaphor, TSAT is analogous to checking the ingredients list and the steps to make sure someone didn't swap the sugar for salt or change the cook time from 15 minutes to 25 minutes. It's not a perfect process, but something's always better than nothing.
So by now, you can probably tell that 3D printer security is an extremely complicated problem, and it requires a lot of research and brainpower. Here at the Auburn Cyber Research Center, we're tackling all sorts of tough problems, such as this. But we do more than that. We're always focused on our students, not just teaching them in the classroom, but giving them real hands-on experience and valuable connections, so that when they graduate, they're ready for whatever industry throws at them.